Okay.
So we are pleased to introduce the course by Professor Stefano Luzzato from SPP on dynamical systems and ergodic.
Thank you very much, Massimiliano. Hello, everyone. Welcome. So I'm going to spend a few minutes giving a little introduction, a little conceptual and maybe even a little bit philosophical introduction. First of all, a technical point is that this is well, let me start by describing what I think is kind of behind this subject. So usually I start with a discussion of the two following concepts. Determinism versus randomness. This is going to be a little bit underlying the subject of the course. This is really what is underlying ergodic theory in many ways. So these words have an immediate intuitive meaning, but in my experience I see that when we start really trying to think of what they mean, things get a little bit more complicated, and I think it would be interesting to think about this a little bit. So can someone give me what they understand as the definition of determinism or deterministic? What do you think? Don't be afraid of making mistakes here.
The initial data determines systems over times.
That's right? This is standard notion of determinism, is that the initial data determines the evolution of the system. What's the definition of randomness? Is it the opposite of determinism? Or is it something else? So determinism is much more complicated to define. So let's look at an example that you're all familiar with. Here's a coin, okay? And we flip a coin. Everybody knows about this case. Is this a deterministic or random process? How many people think it's deterministic? Hands up. How many people think it's a random process? Hands up. Good. I'm always pleased when it's about half and half. So who is right and who is wrong? Well, clearly, from a physical point of view, this is a completely deterministic process, right? This is just classical mechanics. You apply a force to an object, and the outcome is completely determined by the force that you apply. Right? So, if we set a machine, right? So so why do many of us think of it as random? One reason is because it's unpredictable, right? We often tend to associate these two concepts with the concepts of predictability and unpredictability, right? But as this coin example shows, the two things are not really the same. So the reason this is unpredictable is because we cannot control exactly how much force we apply. Right? If you really think of the mechanism, if you put a little machine that gave always exactly the same force in exactly the same place with exactly the same coin, you would always get exactly the same outcome. Do we agree with that? Someone should do the experiment. I don't know, someone's done it, but it's clear that it could be that. So if you think about really how you give the impulse, it's very hard to control exactly how much force you give. And all you need is a little bit. If you think that it's flipping maybe 10 times or so, all you need is 10% extra or less, and it will flip one more time, and so you will not be able to control what's going on, right? So this is a real-life example of a deterministic system, which, however, has unpredictable outcome, right? Unpredictable because we do not have full information. It's not intrinsically unpredictable, right? It's unpredictable because we do not know exactly how much force we're given. It also satisfies, so that's one of the reasons we tend to think of it as a random process, right? In fact, it is not just we think of it as a random process because of its unpredictability, but it's also one of the key examples in probability theory courses or books. Is the first thing is, okay, flipping a coin is the random process by definition almost, right? Even though it's deterministic. So it satisfies another property that we tend to associate to random processes in some sense, which is that if we flip it 1,000 times, we are very likely to get very close to 50% heads and 50% tails. And this is not at all obvious also why this should be. If each time is unpredictable, then why should the statistics of the system be so predictable? Right? If you think about it really, we take it for granted because empirically that's what we see, but the theoretical justification is not at all trivial as to why that should happen. Right? A more sophisticated version of this is the weather, which is also the most standard kind of unpredictable system, right? Which has very well behaved statistical averages, right? The average temperature in Trieste in January is very stable year to year. So this also, why should it be like that? Given it's unpredictable, this is the weather is a completely deterministic system because it evolves according to physical laws. It is unpredictable in the short term. Of course, it's predictable in the very short term, in a few minutes, but I cannot know on Monday of next week at all what weather we're going to have. But it is very predictable statistically on average. All right. So really, this is there are many physical systems that have these kind of properties. There's also many systems that are not unpredictable. Right. For example, the solar system is fairly predictable in the sense that the ancient civilizations also were able to predict, the planets and so on. So it's something to do with the specifics of the systems, which make them, some of them more or less predictable, and those that are unpredictable, many seem to have this long-term statistical predictability. Okay, this is enough of a little philosophical background. The reason I wanted to give this introduction is because we're going to really address this problem, not from a philosophical point of view or from a physical point of view, but just from a mathematical point of view, right? So I'm going to introduce some mathematical systems, introduce the concept of a dynamical system, and describe how we are interested in systems, particularly in my case, in systems which have this kind of short-term unpredictability, that are deterministic, that have short-term unpredictability and long-term statistical averages are well defined, and we're going to try to understand the mechanisms by which this happens, at least in terms of the model. Okay, so this is one of many fields in dynamical systems. So Massimiliano works also in dynamical systems in a different area, probably more related to the planets. Is that right somehow? Or mathematics that is perhaps less to do so much with chaotic systems, but with many other different features of systems that evolve in different ways, different characteristics. There's going to be another course by Stefano Bianchini, also on ergodic theory. His course is going to be much more advanced than this course, so in some sense we have coordinated the two, and I don't think that this would be an essential prerequisite for his, but I think it would be very useful. My course is going to be completely introductory, so I will not assume that you have any knowledge of dynamical systems. Has anyone done already a course in dynamical systems or ergodic theory? Yeah? Yes? Which, in your undergraduate or here? Or?
Only dynamical systems, not ergodic theory.
Okay. Okay. Anybody else? Yes?
Also in the undergraduate.
Undergraduate course in dynamical systems. Okay. Yours. Okay. Okay, so now suddenly we know everyone is an expert Yes. Okay, so I think the field, I would caution you because I like dynamical systems. Part of the reason is that it does not rely on some very sophisticated mathematical machinery, right? But it is very subtle, a lot of subtleties. So the basic setup is very simple, and that's what I'm going to describe. And I'm going to start with some very simple concepts, but don't be careful, because just because they're simple, it doesn't mean they will continue to be simple. And there's things hidden under the surface, okay? So what is the starting point here? The starting point is very simple. We have a set X, and we have a map F from X to X. And this means that we have this is X, this is F from X to X. And in terms of what we were talking about before, we can think of X as the state space of your system. F is the physical law that determines the evolution of the system. And this means that if we take one point X naught as the initial condition of the system, we apply F, we get X naught. X1 equals f of X naught, we get X2, we get X3, and so on, right? So we get what we call the orbit. So the orbit of X naught, I will denote it like this. This is the full future infinite evolution of this particular initial condition. This is called a discrete time dynamical systems. I don't want at the moment to spend too much time on the formal theoretical structure, but if you have an autonomous ordinary differential equation, it gives you a continuous time dynamical system. Like the solutions are continuous time solutions. A lot of the theory, a lot of the concepts, the result, they apply also in that case, but it's much easier to study examples in practice that are discrete time dynamical systems. So I want to introduce some basic examples to study this orbit. So the main objective of dynamical system is summarized here. We define a space X. In abstract setting, this could be a topological space or metric space. In practice, it would be the interval or the circle, it would be some smooth space. We define a map with some characteristics, and what we want to do is describe somehow the structure of all the orbits. It's a very simple setting, right? So, but there's lots of other questions, so you'd like to know, okay, what is this orbit doing? And what is this other orbit doing? What are most orbits doing? What happens if you change this? Does it depend continuously? You know? So there's, of course, lots of questions, but fundamentally, we're trying to understand what these orbits look like. And there are two ways in which we're going to study this orbit. One of them is just we're going to look at it as a sequence, so in a kind of topological setting. A second, which is going to be very important, is we're going to use measures, probability measures, right? And if you think if X is a metric space, then it is both topological and a measurable structure. And then you could, in some sense, you could think of this point as the Dirac delta measure on that point, right? If you take a Dirac delta measure on the point, it defines the point, just as much as defining the point. So you can take the Dirac delta measures in all these points, right? And then we can define a sequence. We can define a probability measure mu n X naught, which is equal to just the average of these Dirac delta measures. This is a probability measure, right? Depends on n. It is a probability measure that is simply equally distributed proportions of the Dirac mass on each one. It's a very simple measure. So if you take n equals 2, it's just half and half here. You know, if you take an orbit of size n, you just put 1/n of the measure on this. And this gives us another sequence, which is the sequence of probability, of these probability measures. Which are somehow becoming more and more spread out along the orbit. Right? But of course you can see that if this orbit is kind of accumulating in some regions of space, then this measure will see this. We'll start seeing where the orbit goes. Okay? So we're going to talk about the topological description. Here you just have a sequence. So we'll be interested in the structure of the sequence, the limit points of this, just as a sequence in a metric space. This will also provide some description of the orbit. And this will provide another description, which is the one that we're mostly interested in. And as we shall see, just this simple fact of thinking of orbits in this way opens up a huge, really a huge door to the kind of things we can say about dynamical systems, which is what makes it very interesting. So I'm going to start by, in dynamics ergodically, examples are fundamental. So I'm really going to start with some examples which seem very simple, but they help to just set out all the definitions and so on and so on. And I'm mostly probably today maybe just talk about the topological part. I don't know, we'll see where we get to. And then tomorrow, look at the same examples from the probabilistic point of view. Okay? So, the very first, I'm going to concentrate first on 3 examples. So example 1 is just very simple family of maps from R to R. And I'm going to take 2 parameters. The simplest possible you can think of. Okay, f of x equals ax plus b. This is just a linear map. And we will study, so in this case, well, let me write down the 3 examples and then we'll study. We'll talk a little bit about what we do. So the other 2 examples are to do, as we shall see from this example, this is defined on all of R, and it's very easy. And actually, before I give the other 2 examples, let me just say a few things about what happens here. So you can see that things depend on A and B, right? So simplest cases, suppose we take A equals 0. If A equals 0, then this is f of x equals b. So this is just a constant function, right? If A equals 1, this f of x equals x plus b. Okay, so in that case, it's very easy to see what happens. So this is x0, and then you have x1 is equal to x0 plus b, right? So you're just adding b each time. This is x2, x3, x0 plus b, depending on whether b is positive or negative. You just get a translation. This is a translation. Right? If b is equal to 0, you get f of x equals ax. What happens in this case? So we take a point x0. Where does it go? It depends on the value of a, right? And it depends on whether x is positive or negative, right? So you can see that we have that x1 is equal to ax0, x2 is equal to ax1, which is equal to a squared x0, and in general we have xn is equal to a to the power n x naught. Right? So this is very easy. Depending on whether a is positive or negative, it's bigger than 1, less than 1. Okay, so for example, if a is equal to 2, then this is just 2 to the n x naught, and it's going to infinity. If a is 1/2, this is 1/2 to the n. Right? So if this is 0, then this may go, if a is bigger than 1, it goes to infinity. As if a is less than 1, it's going to 0. Notice that if a is negative, what's happening if a is negative? It is switching sides all the time, right? Yes. So if a is negative, so let me put 0 here. So suppose a, for example, is between -1 and 0, and then it will be, the absolute value will go to 0, but it keeps switching sides, right? So we have x1, x2, so it does something like this, right? Converges to 0. So really, this family is a bit of a just a toy example, but I will give you some exercises, and I still want you to spend a little bit of time on this, because as I said, sometimes things seem too simple, but they contain some subtleties. For example, what happens? Does this map? Okay, so the key concepts, some of the key concepts we want to introduce, some of the simplest orbits is when we have a fixed point. So definition is that x0 is a fixed point if f x0 equals x0. It's a very natural definition. So in this case, of course, so does this map have fixed points? For which values of a and b does it have fixed points? Or for which values does it not have fixed points? Huh? Excuse me? So if b equals 0 and a equals 1, yes. So if f of x equals x, right? This is the identity map, and every point is a fixed point, right? What about this? What about this? Does this have a fixed point? Yes. When x equals 0 is a fixed point, right? What about this? This is no fixed point because this is a translation, right? Every point gets translated, so it cannot have any fixed points. Okay, so these are very elementary, but again, I really, sorry if I keep repeating this, do not skip over things that look trivial, okay? The best thing is as I introduce these definitions to really try them out in the simplest cases to get a feeling for this, okay? So, a generalization of this is x0 is periodic, is a periodic point if there exists some k greater than or equal to 1, such that xk equals x0. So if it comes back, right? So here we may have that at some point after x3 this comes back to x0. So this is a periodic point with period 4. So a fixed point is a special case of a periodic point with k equals 1. So do we have any periodic points here? Any periodic points for any parameter values?
When a is -1, for instance, and b equals 0, 1 is better.
Exactly. Very good, yes. So when a is -1 and b equals 0, we have f of x equals -x. Right? And so every point is periodic of period 2. So it goes x minus x, except 0, which is still a fixed point in that case. Okay? So as part of one of the very first exercise that I put in the homework is just to do a systematic study of this family of maps, okay? You need to know everything, every parameter, what can happen, right? So as you can see, we've already looked at most of the cases. When it's this kind of situation, then you have everything converges. There's a fixed point at 0, and all the other points either converge to the fixed point or diverge to infinity. Okay? A little bit more difficult is when A and B are both, when you don't have a fixed point at 0, then what happens? Do you ever have, in the general case, do you always have a fixed point here?
Well,
Sorry?
we know that if
Yes?
if A is different from 1, there's always a fixed point.
That's right, why?
There is an equation if you...
Yeah, because the graph intersects the diagonal, right? If you think of the graph, this is just a line, this is just a straight line in the graph, and when it intersects the diagonal, that's a point. So one of the other exercises I'd like you to do is to draw the graphs. So here you have the diagonal, and then you have somehow the graph of this. If it intersects the diagonal, this means that x0 maps to x0, and that's a fixed point. So, okay, so these are the basic fundamental concepts. What is an orbit? When is an orbit a fixed point? When is it a periodic point? So what I'm going to do, the style that I would like to use to teach, is I have some lecture notes that I keep writing every year and I keep revising, which I'm going to follow. So the course is really going to be based on the lecture notes, in the sense that I do not think it really makes sense for me in the class just to go through every line that is in the lecture notes, right? What I would like to do during the lectures is use them to explain the concepts that I think are particularly more difficult, to give the main definitions and so on. But I would not write down systematically all the definitions, all the results, all the examples that are in the lecture notes. Okay? I think that makes much more sense. So the lecture notes are detailed, they have exercises, they have examples, they have all the definitions, and we'll try this at least for a few lectures, see if it's working for you. If you feel that in the lectures I need to be more specific or more careful, then we can change the style, okay? But initially I would like to have that style. So in the lectures I will be more informal and focus on the key points, but that does not mean that you need to restrict your study to this. You need to study what's in the lectures. I will give you precise instructions, delete these sections, maybe not every section of the lecture notes, but I will say exactly these sections, these exercises, and so on, okay? So, okay, and please don't hesitate to ask questions if you have questions at any point. Okay? A small kind of remark about the notation is that when I define the orbit like this, I'm really defining a sequence of points, right? Now, this sequence of points is not always formed by distinct points, right? For example, in the case of a fixed point, these are all the same, so this is really just a unique point, right? So in the case of a fixed point, we have that the full orbit of x0 is just a set x0, right? And in the case of a periodic point, we have that the periodic point of period k is just the set of points x to k minus 1, right? Because then xk minus 1 is equal to x0, and we have this. So this is a little bit of ambiguity in the notation. Generally, the formal definition is as a sequence, but keep in mind that sometimes as a set, this is not always an infinite set. Right? Sometimes it's an infinite set. Sometimes, in fact, there's a couple of exercises that show that if this is not infinite, if this is a finite set, then the point must be either periodic or pre-periodic. So when a map is not injective, you might have some situations in which the point is not periodic, but it falls onto a fixed point. We'll see some of those examples now. Right? So, to develop these concepts further, there's two other examples I want to use as the main examples of the course. And these are obtained actually from this family by a very interesting way. So if we just define same family here, but this time we take mod 1. So this really has a quite astonishing effect on everything, as we shall see. So mod 1 means you just take the decimal part of this, right? So this now becomes a map of the circle. Okay? So when we take mod 1, we are really restricting to the circle. And we're going to in particular look at two cases. So example 2 is the case in which a equals 1. So in that case, we just have fp of x equals x plus b mod 1. So this is sometimes called a circular rotation. Because you can see that here, this is the same kind of circle translation. It's essentially a translation just like we had there. But the difference here, of course, is that when you're on the circle, you start with x0, and then you translate by b, right? So you keep x2, x3, x4, x5, and then because you're taking mod 1, you stay on the circle, and you keep moving around the circle, right? So in this case, it's easy to see that the orbit is given by x0 plus mb mod 1. So I said to you that the purpose of dynamical system is to describe the structure of the orbits. So what's the orbit? Yeah. If you have not seen this example already, could this be a fixed point? When is this a fixed point?
When g is equal to 0 mod 1.
Exactly. Exactly. So first observation is that this really depends only on the parameter, the value of b mod 1, right? Because if b is 1.2, then all it means is that you go around the circle and then plus O2 again, right? So we can assume that b is between 0 and 1, because it's the same thing. If b is bigger than 1, you just go around a few times, but the image is actually exactly the same. And when b is equal to 0, or 0 mod 1, then this is fixed points. Then it's the identity map. Right. Can we have a value of b where you have periodic points of period 2?
When b is equal to 1 over 2.
Exactly. Right? When b is equal to 1/2, then we have x1 is equal to x0 plus 1/2. x2 is equal to x0 plus 1 mod 1, which is just equal to x0. So then it's very easy. So this depends on the value of b. Notice that in this case, every point is periodic of period 2. Right? Okay, so now it's easy. Period 3 equals 1/3, right? When b is equal to 1/3, then you just start from here, you go around 1/3, another third, and you have a periodic point of period 3. So x0 periodic of period 3. How do we generalize this? So what can we say about the values of B? Suppose I tell you that B well, so this means that B 1 over, whenever B is of the form 1 over n, every orbit is periodic of period n. Right? What if B is 2 over 3? Then what happens? Of period 3, right? Okay, let's go straight to the general case. What would be is P over Q?
If Q are in QR coprime is period Q.
That's right, exactly. So if P and Q are coprime, then this is just x Q is equal to x0 plus Q times B. Right? This is the formula we had. You just go by B each time. So in this, with this value of P, this is x0 plus Q times P over Q, which is equal to x0 plus P. Okay, mod 1. P is now an integer, so this is x0. So this is a periodic point. Everybody okay with this? So we've just proved the following lemma, that if B is rational, then every point is periodic. Right, so if B is rational, this implies that every point is periodic, where the period is given by the denominator of the rational number. If you prefer, we can close the curtains actually, if the sun is a bit want to close. It's such a shame to shut out all this sun, but maybe we should turn the lights on, yes. Such a shame. Okay, so what if B is irrational? Let's first of all try to check that you cannot have a periodic orbit, right? So can we show that? Well, let's not do it. I will leave it as an exercise, but one of the exercises shows that if there exists a periodic point, okay, this implies that B is rational. But this is almost trivial, right? If a periodic point, by definition, means that x0 plus nb equals x0 mod 1, right? And so you can easily solve this and show that B is rational. So that means that in the irrational case, you cannot have any periodic points. Okay, we will see in a little while what happens in the irrational case and how we can study that. First, let's stick with the study of periodic points in my third example, which is my favorite example. And this is also this case. Okay, but now we're going to take B equals to 0. And we're going to take a integer value. So I'm just specializing here on this example. This is always this family. What's special about this family is that the derivative is constant, right? This is an affine map. But as soon as we restrict it to the circle, things become very interesting. In particular, I'm going to choose A equal. So this is now f of x equals ax mod 1, right? Where a is an integer. So as we saw before on the real line, this is also very simple. this just goes to infinity or to 0, depending on the value of a. If a is an integer, a natural integer, then it's, if a is 1, this is again just the identity map. If a is 2, this is 2 to the n x mod 1. Right, so it's not so obvious what's going on here. 2 to the n mod 1. And to simplify things, I'm going to choose a equals 10. Because as you see, it shall make it easier. And this is really very, very interesting class of families. So this means that this is f of x equals 10x mod 1. So what is this? What does this map look like? Does it have any fixed points? So yes. Yes, yes. So the key, of course, is a simple observation, but I will spell it out, is that the reason why I chose 10 is because it's very natural using the decimal expansion of real numbers, right? So if you take x0 equals 0.2581 and so on, and you see that it's 1. So multiplication by 10, mod 1 you drop the integer, so you just get 0.5819. Right, that's 2 is equal to 0. So you yes, 819. X3 is equal to 0.19. X4 is equal to 0.9 something. What about X5? It depends on what's next. Right, exactly. Okay, so before going on to study the structure of orbits, I want to connect back to my discussion, earlier discussion about determinism and randomness, right? And say that I think this is a fantastic example of a simple example of a system that is completely deterministic, right? Because you agree that once I fix x naught, its evolution is completely fixed. There's nothing random about it. But look, because of our lack of information, if we knew the infinite decimal expansion of x naught, then we would know the infinite decimal expansion of each of its image, and we would know exactly the whole sequence. Okay? But if we know only part of the decimal expansion, then we always know the next image with increasingly bad approximation, right? So here we know up to 5 decimal places, here up to 4, up to 3, up to 2, up to 1, and we don't even know what's going to happen after only 5 iterations, even though we had 5 decimal places to begin with. Okay? So this makes it unpredictable. This is one of the features, and we're going to study in this course a lot why this kind of system has this kind of unpredictability. If we take another initial condition which is very close, suppose you take y0 equals 0.25821, for example. Right, these two initial conditions are very, very close. Right? If you were taking a measurement of something, you would consider that you had a very accurate measurement. But as you can see, after just 3 steps, y3 here you get 0.21, here you have 0.19, and at the 4th step, you have 0.1 something instead of 0.9 something. Right? This corresponds to getting heads instead of tails, or having a snowstorm instead of a sunny day, whatever, completely different, completely distinct places. Right? So this 10x mod 1, somehow, the fact that we've taken this mod 1 we've compactified in some state of space, creates some really remarkable difference in the dynamics as compared to when you're just working on the full real line here. And as we said from the beginning, so now that we understand this process, it's easy to find the fixed points and the periodic points. So we have lots of fixed points. So for example, x naught is equals 0, obviously is a fixed point. Also x naught equals 0.1111, x naught equals 0.2222, and so on. These are fixed points. Periodic points of period 2. Right, this is easy, so x naught equals 0.252525, for example, recurring. This goes to x1, which is 0.5252 recurring, and this goes back to x1 when you apply it again. So how many periodic points do we have for this map? I think of these as circle maps, but it's easier to draw them as interval maps. It's the same, right? So how many periodic points we have? So we can easily construct periodic points of any period, right? You give me a period 100, I just take 100 decimal places and repeat them, and you get a periodic point of period 100. So we have infinite number of periodic points. Where are they? In the space, it's easy to see that they form a dense subset of the space, right? Because you can approximate any number. If you take any number z, you take it, if it's irrational, you take an irrational point, so it has a non-recurring decimal place. A decimal expansion is 0, a1, a2, and so on, an, and so on. And then you can approximate it by periodic points, right? How do we approximate it by periodic points? We just take the periodic up to an, that's a periodic point, and we can get as close as we want by taking periodic points of very large period. And in this case, because this map is non-invertible, right? If you draw the graph, you see that it has 10 branches. So the graph of 10x mod 1, 0.1, 0.2, looks like this. It's got slope 10, right? And then the mod 1, this is really just 10x, but then the mod 1 means you pull down all the branches, right? So you have this. So you can also see these fixed points from where you intersect the diagonal, right? So the graph intersects the diagonal here. This happens to be, by what we know, this is exactly the point 0.11111, right? This here is exactly the point 0.2222. This is non-invertible. So there are also points that are pre-periodic, so that land on, for example, there is a point that is not fixed and not periodic, but its image is a fixed point. Right? So for example, take x0 equals 0.335555 recurring. Right? And what is the image of this point? This point maps to 0.5 recurring, which is a fixed point. Okay, but this point is not fixed, or it's not periodic, and these are called pre-periodic points. So in fact, pre-periodic points are exactly the rational points in this case, right? Because rational points by definition have an eventually recurring decimal expansion, not necessarily recurring. Right? So the periodic points are rational, but there are rational points which are non-periodic. Right? So the periodic points are already dense, but do not contain all the rational points. If you include the pre-periodic points, then you get exactly the rational points. Okay, so I'm going to do another 5 minutes, then we take a break. I think, I don't know, do you usually take breaks in this class? I think we'll take a 10-minute break in a few minutes. Yeah, let me just say, well, maybe this is a good moment to take a break. Let's take a 10-minute break. Yeah, now it's 5 to 3 until 5 past 3. Yeah, so you can c'è bisogno di possiamo facendo giù lungo abbiamo un po' le tende. Sì, lasciamo un po' aperta lì. Sono persa. Sì,